Now, then we can start. Good morning, everyone. Welcome to Shenzhen IETF 125 Routing Working Group meeting. So let's start with chair's update. We are fully automated, yes. Not well, please read not well. Please make sure you're familiar with all the BCPs and IETF guidelines with regards to conducting yourself. And please don't harass others. Be nice to each other. Meeting tips: if you participate in person, please sign into the session and raise your hand if you are trying to get an talk. For remote, please make sure your audio and video is off. Bandwidth is limited, life is short, so only do it when you're presenting. But isn't it moving? So minutes are collaborative. Please join via Miteka for questions, and please check the notes and minutes before we publish them so we know we are publishing the right thing. And when you are speaking, please state your name and affiliation. We've got, as always, long and full agenda, so please be on time. Don't eat into other people's time. We don't have any new receipts since 124. Why isn't it working? So we've adopted the net notification PS problem statement, and we are looking further how FunTel or Fun with the new name is going to develop. Eventually, we might decide to spin out actually new working group. There's still ongoing discussion on the charter. There's more and more kind of surrounding documents. We've published informational model and data model, and potentially we expect before 126 to start process of new working group. VRRP has been submitted for publication. Thanks, authors, for great work here. A lot of wording. Multi-segment SD1 is working group last call. Actually, working group last call is formally done, given the dates. The authors have responded to all the questions, so I'll do a review during the weekend and continue with further progress of the draft. BGP peak, there are some formal changes. Injink is joining the draft as co-author, and I'll be doing the shepherding. And please review all the new changes. I think Injink did really great work by making it more readable and fixing all the stuff that should have been fixed years ago, but yeah. So there was a meeting with VRRP, the authors. Both draft will be updated. We'll update the working group on the decision taken, but we are progressing with it. The NetCloud problem set has been returned to working group again for, I'm not sure how many times it came back. We need consensus to progress it or maybe not progress it. On QS model, there have been comments from Directorate Review. It's on agenda today. A service with egress protection, I think we reached consensus with the LSR, so it will go in join last call with LSR. And this necessary routing revive, there are some comments that needs to be addressed. And if no questions, we'll start with the first presentation.
Can we get 1 or 2 volunteers to help with the minutes? Anybody? Come on. Yeah, okay.
Your virtual assistant.
That one always works, no complaint, right?
And as a side comment, please send your slides before the deadline. We have a deadline for a reason. We will just not allow you to present if you don't do this.
So for example, I received a slides update request this morning, so I cannot guarantee that I will always see that sort of request. So if you don't submit your slides before the deadline we specify, we cannot guarantee your presentation, period.
And Engine B is nice. He cannot guarantee, I can guarantee you won't. So, QS model.
Yeah, I will be online. Thanks for sharing the slides. Okay, so hello everyone. My name is Asim Chaudhary. I will be providing the updates for QS Yang model. Let me control the slides. Thanks. Okay, since the last working group calls, we have got multiple comments through multiple reviews, and most of the comments have been regarding the refined language refinement and improvement of descriptions. We have taken care of almost all the comments. We have also got some comments regarding the data types which are used in filters and actions. And based on these comments, we are able to update the draft to version 15, which has been published now. So I will try to cover two important comments. First comment was regarding the DSCP range, which, as per the comment, DSCP range may violate RFC 2474. So there was a discussion on the working group mailing chain, mailing list regarding that. And based on the resolution which we achieved in the working group mailing list, we have modified the text in the document to state explicitly that the domain gateway routers has to abide by, has to respect RFC 8436. And for internal domain internal routers, may classify traffic based on the DSCP ranges. Next comment I actually want to highlight was regarding the PHP selection on the nodes. And it was mentioned in the draft that there's no clarification or description, detailed description about PHP selection, where the PHP is selected and who takes what kind of actions. And based on the comment, we have modified the draft to explicitly state that PHP is selected at edge node as well as at the core of the diff subdomain. There's a BI classifier which maps a DSCP traffic to a particular PHP per node, and DSCP to PHP mapping is local to the node. And indeed, multiple DSCP value may map to the same PHP at the single node. And obviously, same DSCP may map to a different PHP when it's a different node in the network. There has been some comments about data model also. And essentially what we have done, we have taken care of those comments. And to list out, we had defined source and destination IPv4 and IPv6, which were defined as a list, but there was a single element in the list. So we have defined it as a leaf list. In addition to that, we had a protocol type protocol in the filter type, which was defined as Unit 8 based on the RFC 9911. We have defined as protocol number as defined in the IETF INET types in the RFC 9911. In addition to that, we had the reference of QS policy, reference of meter reference, as well as the Q reference, which was defined as strings, even though we had defined the templates for those in the same draft. So now we have changed the type from string to leaf ref to the corresponding template for the corresponding reference constructs. So as a next step, we'll essentially double click on the working group last call review comments. We certainly want to address any particular remaining comments which probably we may have left out. And I also suggest and request people from this particular community to review the draft again and pass any further comments. We certainly plan to work on those, and we'll take care of those comments in the next version of the draft. Questions?
I assume the comments you have been addressing are direct review comments. The document
Correct.
hasn't gone through working group last call yet.
Okay, I see. Okay, yeah. Means we asked for last call, but yes, yeah, it still has to make.
So mostly good updates. Drive is now more concise. Please bring it to the finish line. We would really like to start working with last call. It's about time.
Okay, sure. Thank you.
Thank you.
Good morning, everyone. This is Jedong from Huawei. I'm going to give an update on this fast network notifications problem statement on behalf of all the authors and the contributors. So this is a quick recap of the background. For people who are not familiar with this information, we actually, based on the motivation from the AI or machine learning training service, but also considering the requirements from the other cloud-based services, the network need to be more adaptive, can be react faster to ensure the service can be reliable and the congestion-free transferred within all among data centers. And we think what we need is a good and timely understanding of the network operational status, including the congestion situation or the failures, to help improve the network utilization, to reduce the service latency, and enable faster response to other critical events. So this document describes the problem statement of fast network notifications, and it is used as a supporting document for the incubation of the new working group on the fast network notification, or call it FAN. So here are the updates since last presentation in IETF 124. We have received many comments and good suggestions and incorporate them into the current version. We would like to thank to people who have reviewed the draft and contribute to the text. First, here on this page, we list the changes before the adoption call. We have a new co-author, Rashad, and the scope has been narrowed down to fast network notification according to the feedback on the IETF 124 meeting. The structure of the document has also been reorganized to improve the readability. Thanks to Adrian for the help. And the introduction section and also the section 3 have been enhanced with the text about why fast notification is needed and what fast notification means. The description of the existing mechanism has also been revised to be more accurate, like the description related to BFD and the ECN. We also add one subsection about the possible actions. It also clarifies that the action mechanisms themselves are out of the scope of this work. And the security considerations has also been enhanced. And we also received a lot of good comments during the adoption call, and the draft has been revised to address these comments. First, we have revised the abstraction section to address the comments on lossless. I think this now it's more accurate. And we will further clarify that the scope is limited to fast network notification explicit in the draft. And we also mentioned that fast notification applies to a range of network scenarios and topologies, while the solutions for different cases may differ. We also have some text. We also reduce the text in the recipients subsection to focus on the receivers as entities. The delivery mechanism for the fast network notification have been expanded to include the subscription-based approaches. There are also many editorial changes to polish the text. And since this working group document now, a GitHub repository was created for collaborations. Here is the link to the GitHub repository. For now, all the comments or issues have been addressed and the issues have been closed. We welcome your review and further comments either in the mailing list or to the GitHub. Here, I would like to also mention the progress of the FANTEL or fan-side meeting during this week. The goal was to polish the charter text in a face-to-face meeting, which is more efficiently. And we really did that. So we got very good constructive discussions and comments during the meeting, thanks to all the participants. And we also have one agreement on the term or name used for this potential working group, which is the FAN. And we also updated the charter text based on the comments received during the side meeting or before the side meeting on the GitHub. And for now, all the issues have been closed. And here is the GitHub repository link. Please review and continue the discussion on the FANTEL list. And you can also raise issues to the GitHub. So for the next steps, the authors of the problem statement draft will update the draft to reflect the comments received during the side meeting, because some of the scope or some of the description in the side meeting can be used in the problem state draft. And we welcome further review and comments to this draft. Either you can send the comments to the list, raise the issues on the GitHub so that we can reach a relative steady state as soon as possible to guide the future work. Thank you.
Any questions? Jeff, go ahead.
Hi, G, this is Jeff. A very quick comment. The security mechanisms are very likely going to introduce latency into the feedback mechanism. And it's since the security mechanisms almost inevitably slow things down, one of the things that draft should talk about is what the latency requirements are for the feedback mechanisms for this to actually accomplish the desired goal.
Yeah, very good question. I think during the side meeting, people also mentioned this, how much we want to can take the security into consideration in the beginning of the work. We really want to balance this between the security and also the effectiveness of the notification. Yeah, this is something we may consider to revise in the text to reflect this.
So I think we'll happily reuse the definition of limited domains that SRv6 brought, and as long as you are there, no security.
Yeah.
Pretty much.
Yeah, thank you.
There was some discussions about for the charter when we were talking about the domains that technology applies. So the charter will be updated to reflect that.
Yeah, we already have some text about the domains under the single administrative control or we may start from that. Okay.
So yeah, there was some formalization of term limited domain during services work. I think we can reuse it.
Yeah, yeah, sure.
And to add to that, Inge and myself, we started working on data model. So probably sometime next week, we'll publish first revision of data model to kind of formalize all the discussions.
Good.
Any other questions, comments? No, thank you, Jie.
Thank you.
Joy, are you here or online?
Oh,
I guess that.
What? Go ahead, yeah.
Okay. Thank you, Chess. Ladies and gentlemen, I am Roy Zhang from Alibaba Cloud. Today, I would like to present our draft on behalf of the other co-authors. And this draft is about the IP faster reroute for the AI and machine learning fabrics. And this is the first time we present this draft in IETF. So firstly, there is a reminder of the AI backend networks. So the scale-up network, which is the network between the GPUs, is out of scope of this discussion. Let's focus on the scale-out and the scale-across network. The scale-out network typically is a network within the DC, the data center. It has a 2 or 3 tiered folded cross architecture, typically. Sometimes it's leverage the multi-plane and the multi-rail design. And from the perspective of the routing protocol, typically it's run the eBGP. So all of the nodes talk to each other with eBGP. There's no IGP routing protocol. And for the resiliency mechanisms, it's heavily rely on the ECMP to do the fastest, faster switch over. And the scale across networks is another story. Typically, a scale across network is a wide area network, right? So the topology would be more arbitrary, and the routing protocol typically we use the IGP and the BGP. Okay, and as to the resiliency mechanism, so beside the ECMP, we will use the LFA, the loop-free alternative, or TILFA, which is a mechanism rely on the segment routing to achieve the topology independent LFA. And we found that there are some limitations of the existing mechanisms. The first one is the current mechanism is very slow because it depends on the CPU to activate the resiliency mechanism, right? A CPU need to be involved to react to the failure, which will cost around maybe hundreds of milliseconds. But for the AI or machine learning workload, it may need 100 microsecond level faster convergence time. So it's very slow if the CPU is involved. And the second one is all of this current protection mechanism are only handle the local failure, which means only the node suffers the failure can take action, okay? To do the ECMP faster switchover or to enforce the TLFA path. But the ECMP is not always available in the network. For example, in the three-tiered cross architecture, when the packet comes from the ingress leaf to the span, there are ECMPs. From the span to super span, there are ECMPs. But if you go from the super span to the next span, and from the next span to the next leaf, there are no ECMPs. Okay, that's the case of the DC network. And in the WAN or in the scale across network, if you use the TLFA, it will cause the hairpin, right? The hairpin of the traffic, which is not optimal. So that's the second limitation. The third one is all of this faster reroute mechanism cannot handle the case of capacity reduction or the quality degradation. It's work on a binary way, right? It's only between yes or no. But we hope the network can handle the case in a more smart way. It can aware of the different case. For example, if the capacity is reduced by some partially linked failure in a bundle member link, for example, a bundle member link failure, but not instead of a whole bundle failure, right? So based on this analysis, we propose a framework with 4 enhancements to improve the performance of the faster convergence in a fabric for the machine learning and the AI. The first one is the hardware accelerated protection activation. The second one is hardware accelerated network notification. The third one is a mechanism to achieve the complete topology visibility in a BGP-based network. The last one is a quality aware and the remote protection. We'll go through those 4 points one by one. Hardware accelerated protection activation. This is fundamentally is a matter of local implementation, right? It's leveraged the extended NPU capabilities to activate the protection without the CPU involved. So it will be very fast. And we want to say, we hope this hardware accelerated activation could handle both the local failure and the remote failure. In the later case, we rely on the second mechanism, which is a hardware-based notification spread or exchanged within the network. So yeah, that's the hardware-based network notification. So we have seen extensively discussion in the Frontier contest. I will not repeat those discussion. And there are 2 very helpful or useful draft for the statements, problem statement, and some the standardization effort in the IETF. And the third one is complete topology visibility. As you know, in an IGP-based network, the link state routing protocol can exchange the link state information, right? Flooding those information across all the the whole network, and every node have the visibility of the topology, so that it can, make the decision based on the topology to react to the failure. For example, to build the loop-free alternative path. But in a typical DC network, for the AI, for the machine learning, we use BGP. BGP is a distance vector routing protocol. It do not exchange the link state information. So every node running BGP only aware of the topology around itself, not go beyond the next, not go beyond its neighbor. So to resolve this problem, we propose.
Sorry, you have 30 seconds.
Okay, we propose to use the BGP protocol to exchange the link state protocol information, so that all of the nodes can do the TIFA. The last one is the quality-aware remote protection, and that idea is to let the nodes to advertise to notify the failure with different type in more detailed information, so that the other node can react to the failure. Yeah, I think that's basically all of I have for this session, and we are looking forward any feedback from the community. Yeah, thank you.
Great.
Yes, thank you. I heard you right that you said that you need to achieve 100 microsecond switchover time.
Yeah.
Okay, so what defect detection or failure detection you envision to use?
Yeah, well, we expect to to rely on the hardware-based failure detection. For example, the NPU to detect, or the driver to detect any failure of the link in a very fast way.
Well, for example, BFD is implemented with a hardware assistance. Would that be something that you believe will be suitable?
No, because BFD is hardware-based to send or receive the probe, but it still involves the CPU to handle the situation if the keep alive packet lost, right? So you still rely on the CPU, and CPU is the source of the slow processing. So we want to totally bypass the CPU to make the NPU itself to react to the failure.
But how you can guarantee detection of network link failure if there is nothing being transmitted on the link? So
okay, that's another topic. I think given the limited time, we can discuss it in the alias.
Let's take it.
Okay.
Grant, I think it's local implementation detail, and it's a very good topic, right? I think if you look at,
I think it's an interoperability issue, but yeah, okay, let's take it to the list.
Mm-hmm.
Yeah, I agree with you.
Yeah. So in fact, we Changsheng from Channel Mobile, and I think it's a very good presentation. About 1 year ago, we presented another solution very similar to your solution. Maybe we can have some talk offline. Yeah. So,
sure.
Thank you.
Thank you.
Yeah.
Thank you.
As a working group chair, nothing kind of. It's a great pleasure to see all these technologies we've been working on for 20 years coming back home. It's full cycle, right? Started for our work 15, 20 years ago, still coming back. So I really welcome this work. It's interesting. Please clearly separate data center network from one network. If we're looking at what you call scale across, or actually we call scale across, it's nothing else than regular one network. All the technology we've been developing over the years, from RCPT, fast route to TILFA, are fully available. in regular topology, situation is different. You actually know the topology because regular kind of. So focus on complete separation in problem statement and verifying solution for both.
Sorry, I did.
Decouple data center network from one network.
Okay, sure. Yeah, it makes sense. Yeah, we will do that. Yeah.
Thank you.
Thank you.
Okay, let's go to the next François. Okay.
Hey, good morning. I hope you hear me well. I'm François Clad from Cisco, and I'm going to present the efficient remote protection draft on behalf of the co-authors. So that is a fairly new draft. It was submitted a few weeks ago. So it's the first presentation we're doing on it, and we welcome any feedback from the working group. Okay, so that follows the previous presentation, and in particular this efficient remote protection, or the remote protection that is also quality aware. We'll see that more in details through the slides. So I wanted to highlight first two limitations that we have with current IP fast remote technologies, in particular in AI data center, because of all these new requirements that the AI workload imposes. The first limitation is that this is local only protection. So it's only the node that is local to the failure, that is detecting the failure, that takes action to protect the traffic. Of course, the IGP or the routing protocol, IGP or BGP, will eventually reroute, but the point of fast route is to be faster than the IGP and to take care of delivering the traffic in the meantime. So here, and that local protection, it can be ECMP or it can be LFA, and that's great when we have that. But we don't always have an ECMP or LFA available. And then if we don't have ECMP or LFA, then we can use other mechanisms like remote LFA or KLFA, but those can create the hairpin kind of issues, like we see in that example. So we have a leaf L1 that is sending traffic to L2 via a spine S2, and there is a failure from the spine to the leaf, to the destination leaf, and the spine S2 is enabling its TLFA path. It's sending the traffic on the post-convergence path toward the destination, that is via L1, then S1, and L2. That's normal. That's the post-convergence path from S2 perspective. But if we look at it from the perspective of L1, it's not very efficient because we're sending the traffic from L1 to S2, then back to L1, to S1, and finally to the destinations. That's what we are calling a hairpin, and the kind of thing that we want to avoid. In particular, in those AI data center where latency and bandwidth are so critical. And another limitation that we have with the current faster route, as Roy mentioned earlier, is that there is no load on quality awareness. So the faster route reacts to complete failure, but if there is a link degradation or partial failure, then it doesn't react at all. So let's take the example. It's similar to what we had before, but here we are using link bundles, 2 times 10 gigs, so that gives us a 20 gig link bundle. And we have a partial failure on one of the member links from S2 to L2. So instead of the 20 gigs, we only have 10 gigs available. But the leaf L1 doesn't know about that. So it keeps sending 20 gigs and then doing its regular ECMP between S1 and S2. But at S2, we only have 10 gigs available out of the 20 that L1 is sending. And that creates a congestion. Okay, so in order to solve that issue, we are proposing this new mechanism that we call efficient remote protection. So let's start with the failure case, which is maybe easier. So here on the left-hand side, we had the example we used before with the hairpin problem. But if we had a mechanism for S2 to notify L1 that there is a failure from S2 to L2, then L1 could actually act on it and could have a backup path protection for that remote failure. And that protection would send the traffic to the spine S1 directly and then to L2, so that the traffic won't have to go to S2 and then back to L1. Of course, as I said, we need a notification of that failure. So that links back to the work on FAN or FENTEL on fast failure notification. This would be a requirement for those kind of solutions. Before I go to the quality thing and the partial failure, I wanted to highlight something about this failure notification. We had some discussion on Monday during the side meeting about who should receive the failure notification or the network notification. Should it be limited to one hop? Should it go further than that? So here I wanted to highlight one interesting case that in a 3-tier folded closed network, like we can see in some AI data center, if we have a failure between the destination, well, the spine before the destination leaf and that destination leaf, then actually we may need to go 3 hops away to find a remote protection, an efficient remote protection. The problem we have here is that from the local node that detects the failure, so SD1, we don't really have any efficient protection available. We could send the traffic back, but that creates a hairpin. Or we could send it to another leaf and then back to another spine and finally to the destination leaf. But that's not really efficient either. So there is no efficient local protection. If we go back 1 hop to the superspine level, then here we really don't, there is really nothing we can do because the superspine doesn't have any ECMP. It's only connected to 1 spine in each of in the destination pod, so it can't really do anything. Then let's go back 1 more hop to the source spine, or the spine in the source pod, and here we're connected to 2 different superspines, but these 2 different superspines are themselves connected to the same spine in the destination pod most of the time. So again, it doesn't help. And then in the end, the only way to efficiently protect against that failure is to go back all the way to the source leaf, the LA1 in that example. So that means 3 hops away. So that failure notification will need to travel 3 hops. Okay, so then a note on the quality awareness. So if we go back to the example we had before about the quality, so here we have the same partial failure, the failure of a member link of that bundle between S2 and L2 that reduces the capacity to 10 gig. If we send a degraded quality notification, another type of network notification from S2 to L1, then L1 can act on it and can adjust its load balancing so that it no longer sends 20 gigs to S2, but it only sends 10 gig. And then I've been talking a lot about ECMP, ECMP fast route and data center topology, but I just wanted to add that the kind of solution we described in the draft are in fact applicable to any topology. Now, I understand, Jeff, that the requirements in the AI data center and the requirements in the one are totally different. I'm not saying that this is a one-size-fits-all, not at all. I'm just saying that here we have a generic solution, but of course the primary focus for that is the AI data center. And I think I am out of time. So that's good. I reached the final slide. So as I said before, this is the first presentation. It's a new draft. So we welcome any feedback, any comment, any contribution from the working group on that work. Thank you.
Wu Changcheng from China Mobile. So first of all, thank you very much for your presentation. I think we catch the same problem and provide the similar solutions. I send a message through the chat. And please see the draft I mentioned. Maybe we can talk more offline. Thank you.
Yeah, of course. Thank you very much, Wei-Cheng.
Jeff Ventura, NVIDIA's working group member. A couple of observations here, and actually addressed to all drafts previously presented. Please don't forget that there's an extremely robust livability framework implemented on the host. There is, how does host know where to send traffic? It runs congestion control that as of today is RTT based pretty much everywhere. So harpooning is absolutely detrimental to collective performance. If part of your QP goes over longer paths, entire collective will suffer really badly. So we really don't want to do bypasses in this network. Not to forget, it's really equidistant leaf-spine network, so you don't need bypass. Number two, usually we have hardware probes implemented from the host side that are very fast. So normal period would be kind of one probe per RTT. So think about 5 to 10 microseconds. We must make sure the in-network faster route doesn't interact in weird ways with on-host faster route. Some of us remember ATM over IP faster route and what happened when they start to kind of interact with each other. Very similar situation. Make sure the timing is right, not to try to interact with host-based notification, because this is how host changes planes and potentially use different GPUs. So this is not really kind of open knowledge. If you run the AI network, you know this, otherwise not. So I'll try to guide you to the degree I can share with you, but practically keep in mind there's very robust and developed machinery on the host, and network is just think in between. It must not intervene in any healthy way.
Hi, Yale from Citi. A quick question. So in the multi-hop scenario, how do you know, how did the sending node know who are the receiver of the notification? So in the multi-hop scenario, of course, you want to multicast, right? So yeah.
So here, that's a very good question. Thank you. I think part of it will have to be answered by whatever solution we come up with for the network notification. But in my opinion, we would need some kind of a subscription mechanism, a way for the nodes that are interested in those notifications to make themselves known to the sender, so that they can receive them. But again, that's just my opinion on it, and it's a topic that is open for discussion.
Thank you.
As a working group chair now, I believe the answer would come from FunTel or Fun, whether the encapsulation of fast notifications layer 2, so one hop per definition, whether it's IP UDP, which could potentially be multi-hop, or something in between, right? So we would expect this to come from FunTel work.
Yeah. So we'll go to the next presentation. So just a reminder, we do have a very tight schedule. So all the presenters, please try to stay in your allocated time slot, including Q&A, if you are expecting questions. Thank you.
Okay. I will give a brief update of the fair in sound draft.
Try.
Yeah. Changes since the 0.1 version, the dation of 5 causes. Most of them are from GPU vendors. The addition of some considerations on memory semantic operations. Here I will clarify the motivation for this draft. As you know, Ethernet-based scale network has becoming a dominant trend. Here I list some credit examples. In Ethernet scale networks, there are multiple plans with GPU being multi-home to each plan. For the traffic used in the scale networks, it has characteristics such as low entropy, elephant flows, and burstness. So the traditional static ECMP is not applicable in such scenario. Adaptive routing has been widely recognized as a mechanism to improve the load balancing in multi-plan networks. FAIR using BGP is a standard-based adaptive routing mechanism, which was originally designed for scale networks, but it's forward to extend this protocol to scale networks. That means GPU could interchange BGP routings with top switches and then perform adaptive routing. Here I give a concrete example about one-tier scale network. Here, each GPU is multi-home, equipped with multiple high-speed ports, and at least one sub-port is connected to a given network plan. The reason for using multiple links between a given GPU pod and per plan, including it's easy to scale up the size of the superpod. For example, if you need to add more GPUs with a single layer of network, you can use less links between GPU and per plan, and the switches within a given plan. Also, you can add more layer. For example, you add another top layer switches. So that's the reason why multiple links is popular to be used in this scenario. In this example, if there are no link down event happened, then when performing load balancing by source GPU, it will send the same weight values for each ECMP route where each network plan. In case one sublink of a given plan is broken, the ECMP route where that error plan will be reduced by 50%. If the whole plan is broken, then the ECMP route where that plan, the weight will be set to 0. The logic is very simple. It's bandwidth capacity where WSMP, and you can perform per flow-based WSMP or per packet-based ECMP. For flow-based WSMP, it's useful for ordered packet delivery mode, and at least one RDMA queue need to be established between a given BGP pairs for at least one subport. Of course, switches in this scenario need to perform per flow-based load balancing. For per packet WSMP, a single QP is good enough for a given pair of GPU. And in this case, both GPU and the switches could perform per packet-based WSMP, also called packet spraying. When implementing memory semantic operation, we could support 3 modes, such as weak ordering, strong ordering, and passive ordering. Since we provide flexible selection between per packet and per flow-based load balancing, it's easy to achieve the 3 mode requirements. Currently, a POC of 64 GPU superpowered is almost completed, while the 1K GPU superpowered is on the way. Any comments or suggestions?
Jeff, concerning NVIDIA, 2 questions. One, most of the scale-up frameworks mentioned envision non-IP encapsulation. Wouldn't that mean that we would need something like EVPN to provide non-IP identifiers?
You mean there are no IP traffic?
The endpoints are GPU identifiers, they are not IP addresses.
But some GPU vendors can still support IP-based encapsulation.
Absolutely. But again, if you are going through a list of frameworks, most of them envision compressed Ethernet-alike headers. Not really Ethernet, but definitely layer 2. Don't you think we would need something that can allow transport of APEC identifiers, such as CVPN, for example?
Let me try to understand your topic. You mean in a single pair network, you don't need IP-based forwarding?
I'm not saying whether it's needed or not. I'm just commenting on frameworks you've mentioned. Most of them envision non-IP encapsulated traffic.
Okay, let's talk offline.
Sure. Second question, in a single tier, there's no...
Don't too close to your mouse, okay?
In a single tier, there's no routing.
There are echoes, okay. I cannot hear your...
In a single tier, there's no routing, there's no BGP. Practically, if anything, you need some form of fast notification.
No, we are introducing BGP to this scenario. Of course, there are no BGP currently, but we are pushing forward. What direction?
BGP on the host.
Yeah, BGP running on host is common. Even NVIDIA's techno protocol, even NVIDIA's tech stack can support running BGP on host. You can confirm with some of your colleagues. Okay.
Good morning. This is Han Zhengxin from China Unicom. Today, I'm going to share our work on the flow control collaboration across data center networks and wide area networks based on these 2 below drafts. Let's start with the background. Currently, PFC and ECN are widely adopted in data centers for lossless transmission. With the rapid growth of distributed AI training and inference across geographically separated data centers, the demand for congestion-free data transfer has expanded from the DCNs to 1. As we can see from the table, The one is very different from the DCN. It is a enlarged square with a complex dynamic topology and a long RTT. The traffic has frequent macrobursts. So all of this makes significant challenges to achieving congestion-free data transmission. Why not just apply the PFC to one? PFC is a layer 2 mechanism providing the port level feedback for hop-by-hop back pressure over Ethernet. It works well in DCN, but when it applied to one, it has critical limitations, including the head-of-line blocking, dialogues, and congestion spreading. These issues will degrade the network throughput and utilization in one. So to address these limitations and based on the fan-tail problem discussion, we propose the fan green flow control FGFC as an enhancement of PFC designed for IP1. It is a fast, precise layer 3 congestion control mechanism operates in the data plane for millisecond level response. The FGFC enables precise flow control alternates, unlike the PFC port level control, and it limits the flow control to specific paths and slices and provide intelligent congestion back pressure based on the traffic prediction. We can extend the PFC with the network protocols such as ICMP, UDP, etc. to carry this kind of back pressure message. And why we need to consider the co-deployment of PFC and FGFC for data center interconnection over wide area network. It requires to achieve the congestion-free data transfer across data center. As the PFC is already deployed within the DCN, and FGFC is a new mechanism used in one. The edge node R1 and R5 in figures served as the boundary between these two domains need to coordinate PFC and FGFC to achieve the end-to-end flow control. There are two types of the deployment scenarios. Scenario 1 is a single hop direct interconnection. The FGFC message are directly sent between the edge node R1 and R5, so the established tunnel. And the scenario 2 is a multi-hop interconnection, where the intermediate node participate in the congestion control process and depends on the capability of the intermediate nodes. It supports the both hop-by-hop back pressure and cross-hop back pressure. This flexibility makes the compatibility with the existing network device in the critical deployments. And how the PFC and the FGFC interworking from each other. If when the DCN congestion, it triggers the back pressure on nodes in one. For example, when the congestion occurs at data center B, the data center B will send the standard PFC frames to the edge node R5, and the R5 will buffer the affected traffic, and when it reaches the buffer threshold, it will generate FGFC packet with priority AF1, slice ID, and post time, etc. to the upstream node RX. And if the RX cannot resolve the congestion, it will continue sending the back pressure message upstream. Conversely, from the FGFC to PFC, when the one is congested, it triggers the back pressure in DCN. For example, the congestion occurs at node RX, and the RX in the specific slice with the priority AF1, and the RX will send the FGFC packet to the edge node R1 with the AF1 slice ID and posting time. The edge node R1 will buffer the multi-tenant traffic, and when it reaches the buffer threshold, the edge node R1 generates the standard PFC frames for the data center A. Then the data center A will stop all the affected traffic at corresponding port. As the edge node plays an important role for the seamless FGFC and PFC collaboration, below are the requirements. First, the coordination and bidirectional translation between the WAN and DCN flow control, including the protocol conversion, semantic mapping, and policy alignment, and native support for the network slicing. Second, effectively respond to the DCN PF frames. The edge node needs to learn the flow to port mappings and manage the buffer results and generate the FGFC packets for WAN. Third, effectively respond to the FGFC message in WAN. The edge node uses the flow and port mapping relationship to determine the target DNC ports and DCN ports, and generate standard PFC frames for the DCN. This requirement specifies the edge node capability and guiding the device implementation. Besides, we have also done several trials for validation. In Hangzhou, Jinhua, we deployed storage and computing separation AI training over WAN. And in Shanghai, we deployed the distributed inference using the model splitting learning. These trials achieved over 95% computational efficiency compared to the centralized way. And for both trials used FGFC in WAN and PFC in AIDC to guarantee the RDMA performance over long distance. And the gateway devices met the requirements mentioned above for the collaborative deployment, successfully achieving the end-to-end flow control. For next step, we are seeking for more reviews and comments, and we will maintain alignment with Fantail work and related congestion control drafts. Thanks for your attention.
It's very interesting work. Thank you. I have one request for the draft. As you know, buffer space is required to hold PFC message, and there's a formula to calculate buffer space per distance per traffic class. I believe it's 1 meg per 20 kilometers. Yeah, unfortunately. If you could include table on memory requirements based on the distance in the one, that would be very useful for the draft.
You mean, could I put the, oh, sorry. Could you explain, you mean that I put one for the buffer headroom or?
Yeah, based on the distance on the one links.
Oh, so because the distance, like our trails is 300 kilometers. So yeah, we need a big buffer headroom for the device. Yeah, and we have as network operators, we have seen several new devices that with a large buffer. Yeah.
If you could include table on memory requirements based on the distance in the draft, that would be very helpful for people who need to understand it.
Okay, thanks for your suggestion.
At least put some information, maybe as an appendix, if that's
okay.
There is,
Okay, yeah. we will improve our draft. Thanks for your suggestion.
Thank you.
Good morning, everyone. I'm Yisong Liu from China Mobile. And today I will present the multicast use cases for the LM synchronization on behalf of my co-authors. Firstly, I'll introduce the scenario of the LM synchronization in the inference clouds. As we see in the fig, the multi-cloud LM synchronization is that the centralized model repository automatically replicated and synchronized the LLMs to the distributed GPU cloud platforms. And every platform have local the storage. And maybe the GPU clouds in different regions or even in different operator networks. So the immediate inference cloud service will deliver the large-scale real-time inference, fine-tuning, and model optimization services on the GPU cloud platforms. For this scenario, we have two challenges. The first one is the high concurrency. So a popular large model with the size maybe 20 gigabytes to the 1 terabyte. That may be a download simultaneously across dozens of GPU cloud. And this will lead to the input or output bottlenecks at the storage repository, which will delay the model distribution and scale. And the second challenge is that the cold start latency. So the inference service cannot start until the model is fully downloaded to the GPU cloud. And the low download efficiency leads to the significant cold start latency. It will delay the user to access the inference service. So although this synchronization process is separate from the training and the inference procedure, but it will directly affect the efficiency and the reliability of the inference service delivery. So why multicast is needed in this scenario? Firstly, synchronizing synchronizing the largest models to the multiple GPU clouds is a typical multicast use cases. Obviously, it's a point to multi-point pattern. And the second is that it will reduce the I/O bottlenecks from the simultaneous downloads, improve the transmission efficiency, and minimize the cold start latency. The third one is that the GPU clouds span the multiple regions, even multiple operator networks. So multicast technologies capable of operate across the different works, including the core and the metro networks that is required. So for this requirement, we have some candidate multicast technologies. We have a very brief analysis here. For the traditional PMSM, PMSM requires a multicast tree to be established in advance. So all nodes along the tree for every replication path will maintain the multicast flow information. And it is slow to respond to the network topology changes, but it can be improved by the faster reroute mechanism like the MOFR. And it is suitable for the scenarios where the set of the destination GPU clouds is relatively fixed. For the SRP2MP mechanism, this mechanism will rely on the controller to implement the multicast traffic engineering. And the replicating nodes, it means that the replication seed requires a state. The multicast tunnel must be established beforehand. And it is also slow to respond to the network topology changes. But it can be improved also by the faster rerouting mechanism. And it is suitable for the scenarios, also for the destination HPU cloud is relatively fixed. For the beer, beer is as we know, is a stateless multicast technology, and no need to establish a multicast tree, and it will respond quickly to the network topology changes, and no requirement for the destination GPU cloud set to be fixed. So we just initiated the use case and the discussion of this scenario, and we want more detailed requirements and the potential gaps discussion from the working group. Thank you.
Any questions? Okay. You did save us a few minutes. Thank you.
Thank you. If you have any questions and comments, please send to the MCAST to AI, the mailing list. Thank you.
So we do have another one presentation that's also multicast related. So,
Hello everyone. Could you hear me?
yes, we can hear
Yeah.
you. You have control of the slides. Please get started.
Yeah, thank you. Hello everyone, I'm Jie Zhang from China Mobile, and I'm going to present our new draft requirements and gaps analysis of the multicast in AI data centers. Next slide. Next slide, please.
You have
I
control
can.
of the slide.
Okay. Oh, thank you. First, let's see multicast use cases in the AI data centers. And we know the mixture of the experts is a popular model architecture for training and inference, and it's replaced traditional dense models by sparse models with dynamically activated experts. And let's see a macro process of the MOE layers. After computed by the attention networks, a token is dispatched to multiple selected experts decided by gating networks, and each tokens may be routed to different experts. And with experts parallelisms in distributed training of the inference, the token dispatch process may be implemented across different GPUs connected by networks, and the token dispatch process follows the point-to-MP, P2MP traffic pattern, which is a typical multicast use case. So another case is for the LM training. Our reduce is a core collective communication primitives, and the reduce process can be decomposed to the reduce and the broadcaster phrase, where the broadcaster phrase exhibits P2MP traffic patterns, which naturally matching the multicast semantics. And for the task in the AI data centers, besides the model training and inference, there are also the task and of the such as model distributions before the drops start, and the checkpointing savings during the model trainings, and this traffic generated storage networks on the AI DCs. And for the model distributions, it's to distribute the model parameters from the storage nodes to computing node, many computing nodes. And for the checkpoint saving, it's typically written to multiple storage targets to ensure the reliability. So it's also some multicast use cases. And above the from the above multicast use cases, we can see that this exhibits numerous P2MP traffic patterns. And inside of the using many unicast to implement P2MP communications. The using networks communication to offload data replication from the servers to the network devices to implement P2MP communications has many benefits, such as for the processing and the latencies. Multicast can reduce the processing overhead and the latencies of the source GPUs and the source NICs. And then they can enhance the scalability by reducing the source size overhead. And as for transmission and the bandwidth, multicast can eliminate the redundant transmission from the source and improves the receiver size throughput by reducing the bandwidth pressure at the source. And now let's turn to some multicast requirements in data centers. For the first one, interactivities. As we know, P2MP forwarding and data replication is a fundamental functions of the multicast. But for the multicast in the data centers, it's supposed to support the efficient multi-point, two-point MP2P forwarding, particulars for feedbacks such as acknowledgement and congestion signals to meet the ultra-high reliability requirements of the data center networks and to avoid the feedback storms with numerous receivers. The MP2P forwardings are supposed to coordinate with the MP2P packet aggregations. The next requirement is reliability. As we just mentioned, the networks in IDCs supposed to stay the losses and under the normal conditions without networks hardware failures. But when the networks miss network failures such as link failures, multicast mechanisms are supposed to to support the faster failure detection and the recoveries, and for the handling the mechanisms are supposed to confine the impact of the failure to the smallest size of the parts inside of the entire multicast trees. And for the dynamics requirements, the multicast should adapt to the dynamics multicast memberships changes in the microseconds in the scenarios like the MOE token dispatchings. And the multicast should enable the instance forwardings based on the real-time multicast member sections without the needs of the predefined fixed groups. And the changes overhead should be low. As the next requirement is the sparseness. Like as we know, the MOE models is a sparse models. And for example, in the DeepSeek V3s, there are 9 exabytes out of the 200 exabytes in total. the tokens activated a small part of the exabytes in one time. So the smart cards should be efficient for the sparse members identification, and the state maintenance should be lightweight, and effort to considering the ultra high performance requirements of the data center networks. The multicast should be simplicities with a simple control plans and efficient data plans. And there's the gap analysis of the typical existing multicast mechanisms with the multicast requirements in the data centers. For interactivities, there's no native supports for the efficient backwards MP2P forwarding of the packet aggregations, handling the closed loop based feedbacks, and so it's also less less multicast to filter to meet the losses requirements of the data center networks. And for the dynamics requirements, the BERS is relatively good. But for the sparseness requirements, the BERS bit string over high degrees of forwarding efficiencies in sparse member scenarios. And for the simplicities, the mechanism should be optimized for the data center's ultra-high performance. So now the existing multicast techniques can satisfy all the multicast requirements and data centers. The new architectures also deep enhancement to the current techniques are currently needed for data centers. And we seek the feedbacks and welcome the discussions. Thanks for your attention.
Tony, go ahead.
I hope you can hear me. So I already wrote it in the chat, but so I like this envelope, the gap analysis. That's a very good graph. Beer has a solution for the sparse stuff, but of course the size of the sparse group matters. There is a draft you can look up. It's called U-beer for uncompressed beer or something like that. U-beer. Thanks.
Thanks for your advice on the beers. And maybe there's some sparse mechanisms we should also to optimize for the ultra high requirements in the AI data centers.
Any other questions? Okay, thank you for the presentation. Go to
Thank you.
Just a reminder for people in the room, please make sure you scan the QR code and sign into the meeting so we get the right number of people count.
Good morning, everyone. Thanks for the looking area working group chairs for the propositions. Good morning, everyone. Thanks for the preparation by from the chairs to present today in Shenzhen. I'm Ke Minliang from Xidian University. It's my great honor to present our work. My topic is symmetry-driven synchronous forwarding with fast reroute for network near networks. My talk is organized by 5 parts. Microloops are generated during the IGP convergence process and are triggered by link failure and SPF updates unsynchronized and forwarding inconsistency, and which can cause packet loss, congestion, reduce FR effectiveness. The RFC 15715 confirms that microloops prevail in topology changes. This can cause congestion and repair starvation. So the microloops is always in the networks, but how this is starvation in the networks. In neo-cellular networks, due to the more dynamic topology, longer propagator delay, limited onboard resources, so the microloops can cause non-negligible damages. There are 2 drivers. Firstly, plant disruption. Orbital motion can cause ISL changes, and some avoidance can cause laser link shutdown. Secondly, unplanned failure. High energy particles can cause router failures, and software fault can trigger link failure. So in networks, all these changes can need more topology changes, frequent convergence, and more microloops. So microloops have evolved from radical incidents into routine events. This leads to performance disgregation in the networks. Given the challenge, let's think the existing approaches and the onboard limitations. Current approaches such as LFA and SPF timing control are designed for terrestrial networks and fail to fully account for the space elements and constrained resources in their networks. So how can we give this problem in another angle? Our motivation comes from the topology of the satellite constellation. The main constellations such as the Walker Data, Manhattan, and the Twice Manhattan can be abstracted as toroidal topology with rational symmetry and reflecting symmetry. As the picture shows, the Walker Data constellation can map as a torus topology constructed by ISL and can further simplified to a ring topology as a basic unit. So the ring topology is a basic unit of the torus topology. This means we can making rerouting and traffic protection switching into a game grounded in symmetry. Our step mechanism can be explained by example on ring topology. The mechanism is straightforward. Blockage can trigger reverse forward, and the same port triggers reverse egress. For the data packet sent from node A to D, as the picture in red shows, if there is a link error between C and D, then the packet can detour through B, A, G, F, E before arriving D without making micro loops. So how does our step working on a node? The step have 5 procedures. The first is initializing, detecting, trigger RF, forwarding and translating, and then the recovery. All these operations are driven by local state and confirmed symmetry rules on the local node without control plane to participate. So the above is on a ring to introduce. So how does the step scale to towers? We proposed 2 policies: counter first and lateral first, to lead the step scalable to towards forwarding. And the counter first is best for intra-orbit failures, and the lateral first is the best for inter-orbit failures. Compare with existing FR mechanisms, our proposed step have better performance in 3 dimensions: resource, expenditure, convergence speed, and complexity. So we can show that this is a fresh approach to satellite routing. From combating dynamics to leveraging topology. We start our simulation on a 16 multiply 16 towers with different fault probability. The simulation results shows that at the right figure demonstrates that the link failure probability, the packet loss rate change with the link failure probability and the node failure probability. We can see that the many methods LFA and RFA are reduce the packet loss, but our proposed network first demonstrates better performance. And also we have 16.5% reduced under link fault condition and 11.2% reduced under node failure conditions. Next, then we have demonstrated our experiments under a 5-router ring using IPG hardware using standard OSPF v3 with our result step. The experiment results shows that the step we proposed can reduce the peak congestion and can also reduce packet loss caused by micro loop and backhaul, such as the peak congestion reduced from 3,000 Mbps to 2,000 Mbps. To compare with the performance, we have a better packet loss and micro packet loss, and it's better performance in black hole packet loss. We propose a step and under simulation and experiments to prove the performance better than the existing approaches. Let me just summarize the purpose. The step is control plane independent and to delivering the tutorial symmetry for Suan convergence and compare with the existing protocols. It is not modified the existing protocols, so it is easy to use. And that's all. Thank you.
Questions, comments? No?
Any questions?
Okay,
thank you. Thank you.
Hello, everyone. I'm Yisung Liu from China Mobile, and this time I will present the congestion control based on the SRE6 parse. This is the second presentation of this draft. I will give a very quick view of the problem or the background code in this draft. And the first is that it processes the consumption notification in one. So as we know, the traditional PFC relies on the Ethernet multicast. So in the one, we have more complex meshed topologies. So the multicast signal is not proper in this scenario. The second challenge is that the long latency SRE6 path. As we know, the end-to-end SRE path can span large geographical distance, maybe thousands of kilometers. So it will introduce the significant unavoidable latency. The third challenge is that the control overhead as the SRE6 head node. As we know that a single head node maybe will establish numerous SRE6 passes across the one. So there is some centralized bottleneck risk in the SRE6 head node if we make the head node to deal with the congestion control. So that's our SRE6 congestion control proposal for the hop by hop solution. The head node in this fig P1, the P1 encapsulates the seed list from the P1 and P2 and the P3 and the P4. So each node will forward the traffic using the local seed tables, verify the select related info. When the congestion happens, for example, for the P3, it will detect the priority queue buffer overload, and it will send the congestion notification message to the upstream node, in this figure, the PE2, and it will contain the priority queue where the congestion occurs and the congestion control parameter information. This information may be include the post time and the target bandwidth, and must be contain the slice ID. Okay, well, the receiving node, like the PE2, will receive the notification, and it will reduce the forwarding rate or just pause the traffic for this slice. And but maybe the congestion cannot be surprised in this node, and it will detect that the local priority queue overload again. So it will send the notification to its upstream node. And this procedure can can run hop by hop until to the head node. And for the head node, we can use the path rebalancing or the alternative path selection for SRV6 itself. And maybe it will notify the congestion control signal to the DCN. That's another story. So update from the previous draft, we have simplified message format. Because in previous draft we put the SRH in the package format, but maybe some in situation like the bonding seed, like the C seed, it's difficult to distinguish which upstream node we will send the notification message to. So we just give a very simple message format for notification. And for next step, we will add more description, add more procedure for how to notify the path information. So this is just the congestion notification message format, and it will contain the flags. Flags not defined for now, but in the future maybe we can define some special flags. And the priority for the queue priority identifier, each priority queue can occupy the 1 bit. And for the argument, for the congestion control parameter information, like for the post time, for the default parameter, in the future we can define the forwarding rate we want to reduce, and the target bandwidth indicates the target bandwidth information for the expectation suppression. And the slice ID means the identifier for the slice experience the congestion. So we want to seek more review and feedback from the working group. That's all. Thank you.
Any comments, questions? All the discussion happening in the chat. Somewhere in the queue. Yuxuan.
Yuxuan Wang from Tsinghua University. Thank you for your presentation. And here's the question. One of the motivation is that a single head node may be responsible for managing numerous SRV6 paths and placing congestion control at the intermediate nodes can elevate the load on the head node. However, have you considered a scenario where multiple downstream nodes send the congestion notification back simultaneously and receive it at the same upstream node. Could this lead to increased load or excessive congestion control on one of the upstream nodes?
We focus on the SRV6 path, and the congestion control notification just notified one hop by one hop. I don't understand why you say that the multiple downstream nodes.
Maybe repeat your question.
This scenario only for one specific upstream node, is there only one downstream node?
So you mean there is no possibility that multiple downstream nodes send the congestion notification message to the upstream nodes simultaneously?
Every downstream node only sends the notification to the upstream node directly, just to itself.
Okay, I understand. Thank you.
Thank you.
Any other questions?
Thank you.
So given kind of focus and amount of work spent on AIDC, I think we should be considering interim before Vienna. It's a lot of activities, a lot of changes, so we'll notify you accordingly.
So for today's meeting, we have finished all the presentations on the agenda ahead of time. So we did have a small buffer, so now we have the open mic time. If you have any questions, comments to the working group or any future discussion topics, please speak up.
Wake up, it's just Thursday. So thank you everyone for attending, and we'll see you in Vienna, or hopefully on interim sometime in between.
Thanks to David for taking the notes. For people who spoke at the mic, please check the notes to make sure your comments was correctly recorded. And we'll see you in Vienna. If you have some idea for interim or something, talk to us. Thank you.
And there's an fascinating discussion on the list. I mean, not on the list, on the chat. I think we should bring it to the list and continue there. It's a lot of really good points. And I mean, a lot of us have been long enough to have seen similar stuff long ago. So please continue on the list.
我在这里。